Here we are. Sweet. So, as you've heard, my name is Hatfield-Dodds, and this talk is about scaling structured concurrency with static and dynamic analysis. Can I just see a show of hands? Who here understands every word in the title?
Separately or together?
Individually. Like, are they? Do you recognize all of the words? Do you recognize all of them put together? Okay, that's what this talk is about. So, I'm going to give the talk in 4 parts. In the first part, I'm going to talk about asynchronous code in general and what it means for that to be cooperative concurrency. This is just more words that I haven't explained yet. I know that it's coming. Then we'll talk about dynamic analysis, which is broadly speaking, the technique of running your code to check what it does. Then there's structured concurrency, a particular style. And finally, we'll talk about static analysis and code mocks, the techniques of checking whether your code is okay without running it and then fixing it if it's not. So let's start off. The first part, I just want to explain what I mean when I say that async Python is cooperative concurrency. There's a lot of jargon here, which we're going to unpack together. The first thing is that there are a couple of different ways that our code can do multiple things. The simplest way to do multiple things in a program is just to do one thing, then do the next thing, and then do the next thing, right? One at a time. And we call this serial code. Another way you can do it is parallel code, where you just do all of the things at the same time. And the last is concurrent code, where you start doing each thing before you finish doing previous things. So at any given time, you're only doing one thing, but you can have multiple logical tasks currently in progress. And this turns out to be really convenient because it means that your code is not quite such a nightmare to reason about. And it also plays pretty nicely with the global interpreter lock in Python. And because modern computers are typically bottlenecked on waiting for the data to get to the compute, rather than actually bottlenecked on the number crunching itself, this turns out to give you most of the performance as well. So in the form of a diagram, when we have serial code, the green is when we're actually executing something. The blue is when we're waiting for something. And then the red is when we're blocked because another task isn't letting this task run. So in this simple diagram, in serial code, we run task 1, which does a bit of work and a bit of waiting. Then when it's done, task 2 is unblocked and it does some work and it does some waiting, and then we finish. So this is really simple. It's a little slower, but honestly, if you don't really need performance, do this, right? Who here has ever written code which is not performance critical? Who here has ever tried to performance optimize code which didn't really need to be performance optimized? Yeah, a lot of us have been there. So in parallel code, right, we just overlap the whole thing. We say at any given time, we can have multiple things working and waiting at the same time, or working and or waiting. So in Python, of course, this works if you don't have the GIL. People are currently working on removing the GIL, but that turns out to be a pretty hideously complicated thing. It might even slow us down for serial use cases. So I think for many people, the GIL is actually better for them than they quite realize. But the other problem here is now you have to answer questions like, what happens exactly if you try to append a thing to a list and pop the last element of the list at the same time? I mean, literally at the same time, not just say, I would like to do both of these things, and then one happens and then the other. What happens if they happen at the same time? The answer is bad things. Usually this is explained to us with a helpful error message like segmentation fault core dumped. You don't get a traceback, your program just dies. So parallelism can be great for things where it's very carefully managed and contained. For example, the insides of NumPy and of pandas and of many machine learning libraries will be internally parallel. But that's from the perspective of Python, you request one operation, and then your computer does whatever it does, which is internally parallel, and then you get the result. So you get most of the benefits of serial code while your number crunching is still efficiently parallel. And then concurrent work just says you're not allowed to overlap 2 green bits anymore. You can have one task working at any given time, but you can have as many tasks waiting as you like, while 0 or 1 tasks are currently working. So this takes slightly longer for both tasks to complete than the parallel code, but it becomes much easier to reason about because we can think in terms of sort of logical statements about our program. So I like concurrency over parallelism in Python. And then there are 2 kinds of concurrency we can have. One is preemptive and the other is cooperative. Who's heard of these terms before? Several people. You guys are awesome. So preemptive concurrency says tasks can be switched at any time. And I'm just going to say we have a scheduler which is responsible for choosing which task should be executing at any particular time, and not say anything further about the scheduler. That might be your operating system, it might be your async framework, but it doesn't really matter for us. And so with preemptive concurrency, the scheduler can choose to switch tasks at any time, right? This has a bit of a downside in that you have to start putting locks around all of your critical sections. So you have to think really carefully about when might you have things that shouldn't be done separately or that need to be atomic. And this actually turns out to be a lot of the difficulty of threaded programs classically, right? So threads are a classic preemptive concurrency mechanism. In cooperative concurrency, we get just the same speed up overall if we use it well, but we only switch tasks at explicit checkpoints. That is, we have something written in our code which says this is a point at which the scheduler can choose which tasks should run after this point. And so in Python, in async, those checkpoints are actually marked by syntax. If you see the await keyword or an async with or an async for, those are the checkpoints. And so only there can the task switch. So we see a sort of much cleaner setup which matches what we saw earlier. The downside here is that the scheduler can't help you if you forget to write a checkpoint. So if you have a loop that just happens not to have a checkpoint in it, that task is just going to keep running and keep running and keep running. And if it's waiting for results from another task, you have a deadlock, right? So the upside is that it's a little easier to reason about. The downside is it forces you to make sure that you have enough of those checkpoints in there. And so async Python is cooperative concurrency. I just talked about the syntax. We have the await, the async for, or the async with. Does this kind of give you a better sense of why async might be useful? The upside is it's a little easier to reason about. It's a lot faster, especially for things where you want to do multiple logically distinct things that involve I/O, but it's not magic. So let's talk a little about dynamic analysis. This is switching topic a little. Dynamic analysis is where we find bugs by running the code. Tests are a classic dynamic analysis technique, pretty useful. So are writing assert statements in your code, along with the classic have an if statement and then raise an exception, or in some way handle the error. So this doesn't have to be terribly complicated. The reason this matters for us is that if you have cooperative concurrency along with just one uncooperative task, you are going to have a bad time, right? Because the async won't help you if you don't actually write the checkpoint. In this one, task one is doing like some mixture of working and waiting, but from the outside, we can't tell when it's waiting, right? Because there wasn't a checkpoint, or there was a checkpoint, but it didn't make it all the way through the layers of abstraction. And so the net result is it takes us just as long as it would for serial code, except we have all of this complexity overhead as well. So there are a few ways around this. Three specific ones that I like, or two here. One is, who here knows about Python's development mode? 2, 3 people. You guys are awesome. You can run python-x dev or set the Python dev mode environment variable. And this will enable a whole bunch more error checks. Some things for common encoding warnings for text, some things for memory management or garbage collection. It will raise an error if you have a coroutine, an async function, which you never awaited. And so this is just a great thing to enable in your CI system. It's typically a slight slowdown, which is why they're not on all the time, but totally worth it for testing to detect more bugs. And then there's the async IO specific debug mode as well, which will do things like raise an error if one of your tasks goes for more than, I think, 1/10 of a second without checkpointing. So this really helps you discover stuff early in your tests rather than later in production or via Twitter complaints about your service. And if you're using the Trio framework, which is my favorite async framework, Trio doesn't have a standard dev mode like this or warning mode, but it does make it really easy to instrument a lot of stuff. So on the slide here, I have written a complete implementation of a slow task detector, where you pass it your time limit. In this case, I've just said 1/10 of a second. And from that, we calculate the deadline. That is the timestamp at which we should raise an error if a task finished after this point. And we just start that at some ludicrously large number. And then after each task step, we get the current time. If it's after the deadline, we complain that it was too slow, make your test fail by raising too slow error. And then we reset the deadline to limit past the current time. Make sense to everyone? Pretty simple. At work, we also have a neat decorator that we put on very slow synchronous functions. And without looking at the implementation of this decorator, the idea is you're allowed to call it in a sync context, but when you call it, it will do a little bit of introspection to see if it's being called from an async function. And if so, it will just crash. It's like, whoa, I'm too slow. You can't call me like this. You have to delegate me to run in a thread. And then you can await the results come back from that thread. And so this is just a pretty easy pattern that we can put on particular things to make sure that we never get bitten by the same bug twice. Or if we see it coming, we don't get bitten by the bug in the first place. I'm not going to try to go into this one, so come talk to me later if you want the gory details. But async generators interact pretty badly with cancellation because both generators and asynchronous code are different ways of deferring execution until later. And when you inject the cancelled exception into an asynchronous generator, the exception can be delivered to the wrong place in the stack. So the good news is if we ban async generators, which I just did at work, and we test all of our edge cases and we test every possible interleaving of tasks, and we don't mind waiting for these tests to run every time we change our code, dynamic analysis completely solves it and we're done. Async is awesome. Thank you. You're welcome. Okay, there is more to the talk though. So a couple of things here. One, of course, is this gets us through to the point where we understand how to get a bit of a speed up from cooperative concurrency and how to detect at runtime if we've done something that loses us those performance benefits. But writing correct concurrent code is kind of a different additional problem. And that's where structured concurrency comes in. Has anyone heard of structured concurrency? One person. Has anyone used structured concurrency? Two people. Awesome. Structured concurrency is this idea that started with an experimental C library called libdel way back in 2016. So it's a pretty recent invention in the field of software engineering or computer science. It was inspired by Go routines originally. And it was then picked up by a Python library called Trio by one of my colleagues, Nathaniel Smith, and has since become quite popular. So it's now part of the Swift standard library, for example, and support for this is being baked into the WebAssembly spec. So I'm pretty excited that we'll see more and more structured concurrency over the coming years. The core problem that structured concurrency tries to solve is that when you write a program, sometimes things go wrong. And I mean that like in a kind of confined sense, not the sort of cosmic existential, like what is my life? Sometimes things go wrong, but rather sometimes you run a child task and then it wants to raise an exception. And if the parent task is still alive, right? And in CyncPython, it always is, right? When you call a function, the parent function is still there on the stack, right? So if something goes wrong, the exception unwinds up the stack, you get a trace back, and then you either catch it or you crash, but you at least know something about what's going on. In concurrent code, though, if foo calls bar and then foo exits while bar is still running, and then bar raises an exception, what do you do with that exception? This turns out to be a kind of fundamentally difficult problem. There's just nowhere for it to go. And so the common answer in the standard library async.io module and in most other languages is you have a callback that you can register, which just says, I don't know, man, something went wrong somewhere. Here's an exception, I guess. And the default implementation of that is we log an error on the standard error stream, and then we move on with our lives. So I sure hope you weren't looking to handle that exception anywhere important or have any cleanup logic. It's not exactly my preferred style, right? I like Python. I like being able to catch exceptions. And so the idea of structured concurrency is we just say, what if we just ban that? You can't have a child task which lives longer than the parent task ever. And so it turns out that this means that instead of a call stack, we end up with a call tree, right? Each task has a parent task. Each parent task, because we're concurrent, can now have one or more child tasks. Or I guess if it's a leave, 0 or more child tasks. And so we require a little bit of extra syntax for this, but in return, we get a whole bunch of really nice abstraction benefits. The downside is that we now have to enforce this invariant, right? Every task has to finish before the parent task can exit. And that means that we have to have some way of canceling child tasks. In Python, that mechanism is pretty easy. We just fire in an exception. Like there's async io.canceled, there's trio.canceled. You just raise that when you would otherwise resume execution. And so in Trio, anywhere you have a checkpoint is also a point where cancel can be raised. And this makes it pretty easy to reason about when might my task be canceled. It's exactly at the points where another task might run instead. And then there's a bit of a design question here. It's like, well, if one child task here went wrong, like if this bar task failed up here, couldn't we just wait for the siblings to finish and then move on? Why do we have to cancel the sibling tasks? And the answer is that sometimes maybe the sibling tasks are waiting for data from this task. And so if you didn't cancel, you would be prone to just deadlocking as people were waiting for data or for interactions that would just never turn up. So at that point, we've kind of gone through these pretty clear, desirable constraints, and we've come up with a design which is just, we generalize from our stack to a tree, and when things go wrong, we fire an exception to cancel the siblings, and then we unwind back up the tree in exactly the usual way. In Python 3.11, we have a new exception group type, which is pretty much exactly what it sounds like. It's a group of exceptions, one or more. And the idea is that every time a parent task cancels the child tasks or has an error in the child tasks, you then wrap those exceptions in an exception group at each point where the branches come together. And this means that you can actually handle those exceptions again. You can inspect them in all the usual ways. And you don't have to worry about, did I remember the weird special case where two things went wrong at the same time? Because if two things could go wrong at the same time, you'll have an exception group, even if it only has one child error in it. This turns out to give us another really nice thing as well, which is great support for timeouts. In this model where we have structured concurrency, conceptually a timeout can just be a task that waits us for a certain amount of time and then cancels another task, right? That's how a timeout works. And this means that you can wrap timeouts around arbitrary subparts of your program. So it's really nicely composable. But why do we want timeouts in the first place, right? We might be doing something like acquiring a lock or sending a request. And there are basically three things that can happen here. It can succeed. That's the happy path, and pretty much everyone handles the happy path. It can fail, and if we're in a good mood, sometimes we remember to handle the unhappy failure path. But it can also hang forever, right? My colleague wrote, days pass, leaves fall, winter comes, and our request is waiting and yearning for a response that will never arrive. I feel kind of bad for it, to be honest. But it's not a kindness to that task just to leave it waiting forever. So a timeout lets us kind of exert some control over the outside world, right? There's no way to say the server absolutely must respond within 60 seconds. Sometimes it won't, and there's nothing you can do about that. But you can decide that 60 seconds is the longest that we're willing to wait. So quick pop quiz. Has anyone here used requests? More than 3 hands. I'm back on the happy path. All right. Has anyone passed the timeout argument to requests.get? Fewer people, but still some. What is the largest amount of time that this code on the slide can take? I have a vote for 5 seconds. Any other takers? Milliseconds? No, the unit of this timeout is seconds. That's a good thing to note, but in this case, it is seconds. Any other guesses? Not entirely bounded. It can indeed be a lot longer. So the timeout argument to request turns out to be, by the time you've traced it all the way down the stack, this is the socket read timeout. So under the hood, request.get will open a Unix socket to whatever server and start requesting bytes, right? So the HTTP packets will come over, you'll read the packets, you'll reconstruct the response. And if at any point you wait for more than 5 seconds without receiving at least 1 byte from the server, you'll raise a timeout error. But if the server decides to send you 1 byte every 4 seconds, they can keep you waiting for an awfully long time. And this is, in fact, a pretty practical denial of service attack that people mount on web servers all the time. It's more common to attack servers than clients this way. So let's look at a different style of timeouts. I talked before about the idea that you can wrap a subtree of your structured program in this way. So we say with trio.fail after 5, await client get that URL. How long can this take in the worst case? 5 seconds. I have votes for 5 seconds. Anyone else? Okay, I'll put you out of your misery. This can take just a little bit more than 5 seconds, right? So what this will do is it will raise the too slow error after the first checkpoint that we reach after 5 seconds has been exceeded, right? So if we reach the 5-second timeout and our subtask is currently waiting, then we'll finish whatever other task was running. And when we next go to run this task, to check that socket again, for example, that's when we'll raise the too slow error. So because it's cooperative concurrency, right, we're not guaranteed that the scheduler will be able to immediately cancel it when 5 seconds is exceeded, but we are guaranteed that the task won't be allowed to start from a checkpoint after that 5-second deadline. And in practice, that's a pretty good trade-off. So is this readable from the audience? Slightly? Okay. Okay, we at least have people who raise their hands when instructed to do so. Hopefully they can also read this. This is a complete two-way echo server using structured concurrency. So we've organized it into 3 functions, and it has nice handling for all of the edge cases, including timeouts. The top function, which you may be able to recognize by shape, is a one-way proxy. We pass it a source and a sync socket, and we say while data walrus operator is await source receive up to 1024 bytes, send all of those bytes that we just received. And when we receive an empty byte string, which is the convention for the socket is finished sending things, then send the end of file and then return from the function. And we don't have any handling for timeouts here because that's a concern for a higher level of abstraction. Then our two-way proxy, we have a trio nursery. So that's this context manager. We say async with trio nursery as nursery, start soon a one-way proxy in one direction and start soon a one-way proxy in the other direction. So we've kind of just glued them together. Anything you put in one side will pop back out the other. And then in our main function, we open a move on after context manager. This is a timeout, but when we reach that deadline, instead of failing, we just cancel the things internally and then move on without raising that exception. We open 2 TCP streams and then using those in a context manager so that they close properly when we're done, we await the proxy two-way, and then at the end, we print all done. So this is a pretty convenient way to do it, given that we have proper handling for timeouts, exceptions, cancellation, and so on. And then the last part of my talk, I'm assuming that no one wants to ask me questions about this little server. Yeah, no, okay. Static analysis. Who here has used a static analysis tool? Who here has ever used a type checker, a linter, a spell checker? Those are all static analysis tools. The key feature of static analysis is that it checks something about your code without actually executing it. So this can be very, very simple in some cases. Just regular expression, for example, is quite a popular way of doing static analysis, up to like super fancy type theory stuff. One pretty easy way to add your own static analysis is with something like Flake8 or Pyland. I personally like Flake8 because it's so easy to write plugins for it. The idea is you get the abstract syntax tree of your code, which is this nice structured representation of how the code is passed, but it ignores things like comments and white space and parentheses. So you can look at just the logical structure of your code without having to care much about how it's formatted. And then you can do things like say, if I call a function named this with arguments like that, raise an error. It's pretty easy to write them, but it doesn't fit on one slide like the server did, so I'm not going to show you a complete implementation. I recently built, along with a friend, a plugin called Flake8 Trio, which detects a whole bunch of problems in async code. I won't go through all of these in detail, but some of the things like if you have a timeout context with no checkpoints in it, that's pointless. The timeout can never fire, so you probably have a bug of some kind. Or you called time.sleep in an async function. You should probably not do that because we have async sleeps and then your code can do something else while we're waiting. A whole bunch of other common sort of paper cuts or simple mistakes that we saw regularly at work or in other open source code that I was working with. And a logical extension to this is to say, well, if we can recognize patterns which have some kind of problem with our code, sometimes people say that the mark of a a great programmer is laziness and impatience, right? You don't want to do any work, but you still want the job done to be done quickly. And so there's a tool called libcst by the fine folk at Instagram, which is designed to be pretty similar to the abstract syntax tree, but it also tracks things like the parentheses, the white space, and comments, so that you can actually modify the code, rewrite it in place, do that kind of structured analysis in a very convenient way. So to demonstrate that, I wrote a small fix. I mentioned we have this async function f, and all it does is it sleeps for a while. And this is, of course, something like a tiny, very concentrated worst practice. Don't do this at home. Especially don't do this at work, colleagues. So how do we fix this? Well, we import a bunch of stuff that you can see on my slides later. And then we declare a couple of matcher methods. So this says we want to call this method if we're inside a function def, which is asynchronous. With me so far? Yep. Then we say the thing we want to look for is a call where the thing we're calling is time.sleep. Still with me? I see some nods. And then we say the function that we want to do, right, that we're going to replace is we're going to create a new thing, trio sleep, which is trio.sleep, because we're using the trio library. And then we're going to return await that thing, right? But we're going to take that node that we started with and just change what function we're calling, right? So time.sleep, whatever, with the same white space, the same parentheses, any comment that we have, we're going to have exactly that same thing. But now we're going to replace time.sleep with trio.sleep, and we're going to await that. And there we are. This runs automatically. That was complete working code. And you can replace it in your entire code base. I found more in our code base than I really like to think about. Some things got literally 8,000 times faster. We were sleeping for 1 second to make sure that things happen. Also not a great pattern, use events. That's a different lint rule. But this, if you are going to sleep, is the way to do it. So to recap, we've covered 4 things, right? I've described asynchronous code as cooperative concurrency. Who here feels like they know what that means now? A few more people. It's encouraging. Dynamic analysis. Does everyone remember what dynamic analysis is? Give me an example. PyTest, running a test, assertions. Awesome. Structured concurrency. Some nods. Do we like it? Do we not like it? What's a key advantage of structured concurrency? Exception tracking. Awesome. And I've just told you about static analysis and code mods. So, questions? If you were at PyCon, I was indeed around in the hallway tracking out the sprints. This time, I think I'm going to take questions right here. So thanks very much.
So I use timeout with, and I can't remember the exact method or oh sure, sorry. So I use timeouts with standard library async. What are the what guns I'm not seeing, or
yeah,
why should I use trio? I guess is my
Great question. So the main difference between the standard library async.io module and trio is that async.io does not enforce structured concurrency. So if you use async.io and you have an exception, it may or may not get propagated, which I'm not a huge fan of. In Python 3.11, the standard library added the task group context manager, which is pretty similar to a trio nursery. The key distinction there is still that in async.io, cancellation works very differently. In trio, if you cancel something, the entire task is canceled as a state change. In async.io, the cancellation semantics is it raises the canceled exception once, but if someone happens to catch that exception, execution can just continue. So there's actually not a reliable way to cancel something in async.io. The other side, of course, is that the async.io ecosystem is mostly predicated on earlier styles of concurrency. So if you want the structured concurrency semantics, it kind of relies on that composability being present right through your stack. And async.io, you can opt into part of the composability in some places, but I think trio still has some really big advantages. I'm excited, though, that the standard library is getting more of them over time.
Have you had a chance to try AnyIO?
AnyIO is great. AnyIO is a compatibility library, which basically gives you the Trio API or something very, very close to it, which can run on top of either Trio or on top of async IO. So if you're implementing async libraries, I would encourage you to use any IO. If you're using it at work, I considered using any IO, but I thought, well, I might as well cut out a single call frame and use Trio directly.
So you talked about how you use dynamic analysis mostly for performance tracking.
Yep.
Do you also do any dynamic analysis for correctness checking, or is it only for performance?
Great question. With respect to structured concurrency specifically, it's mostly performance. And I also sprinkle assertions through my code, but those are mostly for logical invariance because the framework itself enforces most of the structure and the concurrency I would need.
So one of the things that's held me back from using more asynchronous stuff is my impression is you have to have those checkpoints all the way down the stack. Is there a way to incrementally move one's code in that direction? So you can do bits and pieces and get at least some of the benefits of what we're talking about.
Yep. So the simple version, if you're using Trio or any IO, is they have a 2-thread function where you just say like, here's the sync function I want to run it for me in a thread, and then I can just await that. And when the sync function finishes running in a thread, like bring the result back for me. And so that's often a great way to kind of take a big chunk of work, right? So you're not at this like super granular level. The cancellation semantics are usually just like the thread keeps running in the background, but we ignore the result when it eventually turns up. So some downsides there, but it does make it a lot easier to migrate. If you have like a request handler, you can now say like, okay, I'll make the outer part of the loop asynchronous, and then like I'll just run my existing request handler for each request that turns up, and I'll run it in a separate thread. I've also just used this technique a couple of times. Like when I was doing a mock interview a while ago, I'm like, I kind of want to use Trio for this, but they already have their like fetcher thing from the web helper. Fine, I'll just run that in thread, no problem. So I got to use all the nice async syntax and timeouts and so on without having to rewrite their entire handler.
Thank you.
I got a question. I won't share the mic with you. So this is good about obviously to make the best use of your processors. But if you have something that is not exactly the same core replicated, like if you have things like simultaneous multi-threading, also known as hyper-threading, and different core configurations, is there any comments you can make on using this in those environments?
Yeah, I think my meta comment is if kind of the core of your performance problems is you need really fast computation on multiple cores for something kind of number crunchy rather than waiting for IO, Python is probably just the wrong language for that. Like, I like Python a lot. I do some hilariously number crunchy things, but the way I do it is I call a function which runs something on the GPU, right? And then my async code waits for the results to be ready on the GPU and then sends the next thing to the GPU.
Or maybe I would say use Python, but use the language interfaces. So you write the lower level. Yes.
You use
don't have to switch, you don't have to switch to Go.
Of course,
but
like
yeah. So
my favorite way to write performance critical code in other languages is to call it from Python.
Exactly.
Right. But at that point, like the number crunching is not in Python. The number crunching is in a different thread or a different process, and I interact with that asynchronously.
Exactly. Okay. All right. Thank you. Any other questions? I think that's it. All right. Well, thanks, Zach. That was excellent.
Thanks very much, everyone.